Hi guys, let's practice drawing some molecules that do not obey the octet rule. So we're going to start first by the ones that have less than an octet, less than 8 around the central atom. And you will know these just because there won't be any other electrons to bond more. So for example, beryllium has 2 valence electrons. I'm going to put them on each side here. It's bonded to 2 hydrogens, so there's a hydrogen and there's another hydrogen with their 1 electron each, and so you bond them and then you're stuck. That's it. Hydrogens are good with the duets, but beryllium has 4, and there's no other way that you can add a double bond or anything like that, and so that's it. There's nothing else you can do. Electron geometry, there are 2 areas of electrons, so this is going to be linear, which means the bond angles are going to be 180. And the hybrid is going to be Sb. The molecular geometry, you have your beryllium surrounded by 2 things at 180, so that is also linear. Or you can say, since the central atom doesn't have any lone pairs, then the electron and molecular geometry are going to be the same. And this one is nonpolar because the arrows would cancel each other out. Okay, Bf3. Boron has 3 valence electrons. Each fluorine has 7. And so you bond everything once, and that's all you can do. You can make it look a little bit nicer if you want. You know, it would look like this. So the electron geometry, 3 areas of electrons, so that's trigonal planar. Bond angles are 120. Hybrid is sp2 because there's 3 areas of electrons, 1 has 2 p's. And the molecular and the electron geometry are the same because you have no lone pairs on the central atom. Or you can say there's a boron, 3 things coming at 120, that would be trigonal planar. This one is nonpolar again because the arrows would cancel. Let me go ahead and draw the arrows for you. So you'd have these 3 there and they would all cancel. Now, in order to recognize that these do not obey the octet rule, some of them are obvious, like this one, just no way to do it. This one also, there's no way to do it, except I guess if you do a coordinate covalent, like if you share those here. But if you look at a periodic table, usually group 2 and group 13 are the ones that would do that. That would be in less than an octet. Not all the time, but you know, most of the time those are the 2. Now the ones that form more than an octet, or an expanded valence is what we call it, those are easier to spot because there's just not going to be any other way again. So let's try to do some of these. So we have a phosphorus. Each phosphorus, the phosphorus has 5 valence electrons. It has to bond to 5 fluorines, right? So, I mean, there's no way to do this except to bond to 5 fluorines. So from each of these bonds, one of the electrons is coming from the phosphorus, the other is coming from the fluorine. Fluorine has 7 total, so 1 in the bond and then 6 in lone pairs. So I'm going to draw the rest of the lone pairs here. Okay, electron geometry. So this one has 5 areas of electrons, and so trigonal bipyramidal. My angles would be, we have 90 and we have 120. My molecular geometry would also be trigonal bipyramidal. You don't have any lone pairs on the central atom there. 5 things at 120 and 90. And this one is nonpolar. If you look around your central atom, everything is the same. Or if you draw your little arrows, I'll draw them for you if you want. There we go. They all cancel each other out. Remember, so when you draw this, there's one up, one down that are 120 from each other, or sorry, 180 from each other. Those cancel each other out. And then in the plane of the paper, the rest are 120, and those 3 cancel each other out. Okay, SeCl6. So selenium has 6 valence electrons. It has to bond to 6 chlorines. So there's no way that you can draw that without giving this an extended octet, right? Like there's 12, just like this one, there's 10. There's nothing you can do about it. You have to bond to 6 chlorines, right? So selenium has 6 electrons, 1 in each of the bonds. Chlorine has 7 each, so 1 in the bond and then 6 that are in lone pairs. I don't know why some of my dots are light and some of them are thick. It's really odd. These are 6 lone pair, or 3 lone pairs there. It's kind of hard to get them. All right. Electron geometry. So you can call this an octahedral or a square bipyramidal. We'll just go with octahedral. Actually, I'll write both. They're such fun names. The molecular geometry is the same because you don't have lone pairs around it. 6 things, all at 90 degrees. And this one is nonpolar because it's symmetrical. All of them would cancel each other out. They're all 90 degrees apart and they're pulling with the same strength. Just a reminder, we don't do hybrids for anything above sp3, so you wouldn't have to worry about this. Okay, XEF2. Let's try that one. So, xenon has 8 valence electrons. It has to bond to 2 fluorines. So, now let me do a different color. There's your Xe. 8 valence electrons. It has to bond to 2 fluorines. So there's one. There's another one. Let's clean it up a little bit. Make it look a little bit nicer. You have to put your electrons in pairs, right? So put a pair here, a pair there, and a pair there. Okay, 5 areas of electrons. So trigonal, bipyramidal. But we have 3 lone pairs. So the bond angles normally are 90 and 120 for that, but it's not in this case. In this case, so normally you'd have like, you know, 1 up, 1 down, and then these are 120, right? Well, we don't have any of those. So what angle does that make? That is 180. And it is linear. And it's actually nonpolar. This is one of the very few that you will see where it has lone pairs, but it's nonpolar. That's a really tricky one, just because of the placement of the lone pairs and the placement of the bonds, because since it is linear, this cancels with that one because they are 180 apart from each other. So that's a tricky one. XEF6 is the last one we're going to do here. So xenon has 8 valence electrons. We got bonded to 6 fluorines. Well, that's a lot. 2, 3, 4, 5, 6. And then fill them in. So that's all we can do. It has way too many, right? It has what, 14 electrons, but there's no other way that we can draw this. 7 areas of electrons, so that's a pentagonal bipyramidal. So you have like 1 up, 1 down, and then 5 that are kind of like 72 degrees apart, I guess. So 90 and 72 are angles. The molecular geometry in this case is a pentagonal pyramidal as opposed to bipyramidal. Just pyramidal. So we don't have, you know, the one that's down. We just have the up and then the ones that are all in a plane at 72. This one would be polar. And so if you draw all your arrows, they don't all cancel because you don't have the one on top to pull. And so the net would be looking this way. All right, last thing we're gonna mention here. This used to be a popular question on the AP exam. It is no longer a popular question. I wouldn't worry about it too much, but just in case it shows up. You know how like we have PF5? We just saw that right here with an expanded valence. You can never have NF5. And the reason used to be, if you remember, like when we did the hybrid, we'd say that this is an sp3d. So phosphorus is in the 3rd period. And so it has the sp3, that's the 8, and then we can put the 2 extra electrons into the d orbital. Whereas nitrogen is in the 2nd period, there is no 2d, and so you don't have room for that to happen. Now that the hybridization where D is involved is no longer accepted, if you were asked why NF5 does not exist, you say because of steric hindrance. So no too much steric hindrance. What does that mean? Steric hindrance means crowdedness of electrons. That's what that means. So basically we're saying nitrogen is too small to be able to handle, you know, 5 electron clouds around it. Those would repel each other too much. Whereas if you have phosphorus or something larger, then you can handle, you know, the 5 different things. They're not, you know, so close to each other, they're not as crowded, and so it will allow for this to happen. So I doubt this would be a question on the AP exam, but if it does, you just say nitrogen is too small, it doesn't allow for 5 things to be around it, the electrons are too crowded. Or if you want to sound fancy, you can say because of steric hindrance.